Meta and Harvard just built a code agent that actually works on massive real-world code bases, the kind of millions of lines that normally make AI tools completely fall apart. We're talking about the Confucius Code Agent, and the performance numbers behind these things are honestly surprising. So let's talk about it. Alright, so the Confucius Code Agent comes from a team split between Meta AI and Harvard researchers. And the first thing you need to understand is what gap they're actually filling. Most AI code tools today work great when you are writing a single function or fixing a bug in one file. Tools like Cursor and GitHub Copilot are built for that. But the moment you step into a real company code base, something with hundreds of thousands of lines spread across thousands of files, these systems just break down. They lose track of what they were doing. They can't remember what happened 50 steps ago. And they definitely can't coordinate complex workflows that involve editing 10 files, running tests, checking errors, and fixing issues across multiple tries. That's exactly where CCA was designed to work. Here is the thing. CCA isn't built around a bigger model or more compute power. It's built around something the researchers call the Confucius SDK. And that SDK treats agent design as a real engineering problem instead of just warping a language model with some basic tools. The SDK is organized around three different angles. Agent experience, which controls what the model actually sees and how information gets structured. User experience, which focuses on reliable logs and safe outputs for human developers, and developer experience, which gives people building agents the tools to actually debug, test, and improve their systems. Most frameworks only think about one of those angles. The Confucius SDK treats all three as equally important, and that separation turns out to make a huge difference. Now let's talk about the actual performance, because the numbers tell a clear story. On SWE-bench Pro, which includes 731 real GitHub issues that require modifying actual repositories until the test pass, CCA with Claude 4.5 Opus scored 54.3%. That's state of the art for open source agents. And when you compare that to prior research baselines, CCA beats them all. On SWE-bench Verified, which has 500 verified tasks, CCA with Claude 4 Sonnet hit 74.6%. And honestly, what makes this even more interesting is that all these systems were tested under identical conditions. Same repositories, same tools, same evaluation setup. The only difference was the agent design itself. The researchers also ran a really interesting comparison that shows how much the scaffold matters. They tested Claude 4.5 Sonnet with CCA and got 52.7%. Then they tested Claude 4.5 Opus, which is a stronger and more expensive model with a simpler agent setup, and it only scored 52%. Think about that. A mid-tier model with a well-designed agent beat a top-tier model with basic tools. That result alone flips the whole conversation about AI coding tools, because everyone's been focused on which model is biggest and smartest. But this shows that how you structure the agent, how you manage memory, how you handle tools, all of that matters just as much, maybe even more. Now here is where it gets interesting. The way CCA actually works comes down to four main pieces. The first piece is hierarchical working memory. Most agents just keep a running list of everything that happened in the conversation. But when you are working on a big code base and the session goes long, that list gets massive and the model starts losing track of what's important. CCA instead uses a layered memory system. It organizes information into different scopes, like Session 1 memory for overall task, entry-level memory for specific steps, and runnable level memory for individual tool calls. Then when the conversation gets too long, a special planner agent called architect kicks in and compresses the older parts into a structured summary. That summary includes goals, decisions, errors, and open tasks, but it strips out all the noise. This keeps the prompts clean and focused, which means the model can actually reason clearly even after hundreds of steps. The second technique is persistent note-taking. After each session, a separate note-taking agent goes through everything that happened, the user messages, the tool calls, the outputs, the errors, and writes a structured markdown note. These notes capture what worked, what failed, and what patterns showed up. Then in future sessions, CCA loads those notes into memory right at the start. The researchers tested this on 151 tasks with Claude 4.5 Sonnet. On the first one, the agent solved tasks from scratch. On the second one, It read the notes from the first run. The results were clear. Average turns dropped from 64 to 61. Token users dropped from about 104,000 to 93,000, and the success rate improved from 53% to 54.4%. That's a 1.4 point jump just from reusing knowledge across sessions. That notes basically act as long-term memory, letting the agent learn from past mistakes instead of repeating them. The third component is a modular extension system. CCA doesn't have tools hard-coded into the agent. Instead, it treats tools as plugin extensions. Each extension handles one specific thing, like file editing, running cell comments, searching code, or executing tests. These extensions can maintain their own state and have their own prompt running. And because they are modular, you can swap them out or add new ones without rewriting the whole agent. The researchers ran an experiment to measure how much tool design matters. They tested on a 100 task subset of SWE-bench Pro with Claude 4.5 Sonnet and simple tool handling. The agent scored 44%. When they switched to richer tool configurations, the score jumped to 51.6%. That's a 7.6 point improvement just from better tool use. With Claude 4 Sonnet, the jump was even bigger, going from 42% without advanced context features to 48.6% with them. These numbers prove that how you design tools isn't just an implementation detail, it's a major performance driver. The fourth piece is the meta agent, and this one is honestly kind of wild. Most agents are hand-tuned by humans. You write prompts, set up tools, tweak settings, run tests, and repeat until it works. That process is slow and doesn't scale. The Confucius SDK includes a meta agent that automates this whole loop. You give it a natural language description of what you want the agent to do, and it builds the agent for you. It processes configurations, writes prompts, selects extensions, runs test tasks, checks what broke, and then refines the setup. CCA itself was built using this meta agent process. The researchers don't hand-tune every prompt. The meta agent synthesized and improved the configurations automatically. This gives developers a huge advantage because they can rapidly create new agents or adapt existing ones to new tasks without spending weeks on manual tuning. To be clear, CCA isn't perfect. The researchers were upfront about limitations. One area where it struggles is tasks that need deep domain knowledge, especially when the codebase uses custom business logic that isn't documented anywhere. It also has trouble with poorly structured code, projects with inconsistent naming or missing comments, because the memory system relies on being able to parse relationships between files. And while CCA handles most tasks well, there is a noticeable drop in performance when it has to edit 10 or more files at once. The paper mentions that on tasks requiring changes to 10 plus files, the resource rate drops to 44.4%. That's still decent, but it's not as strong as the overall 54.3% average. The team is working on improving multi-file coordination, but it's known limitation right now. Another challenge is token efficiency. Even with hierarchical memory and compression, some tasks still end up using a lot of tokens. The researchers reported that enabling context management reduced prompt length by over 40% in many cases without losing important information. But there are still edge cases where the memory system doesn't compress well, especially on tasks with lot of back and forth debugging. They're exploring ways to make the compression smarter, but for now, it's a balance between keeping enough context for the model to reason and staying within token limits. In fairness, what really stands out about this work is how transparent everything is. CCA is fully open source. The orchestration logic, the prompts, the tool stack, everything is exposed. That's rare for systems performing at this level. Most commercial code agents are black boxes. You can use them, but you can't see how they work or modify them. With CCA, researchers and developers can dig into exactly how it makes decisions, run their own experiments, and customize it for specific workflows. The paper even includes detailed ablation studies showing what happened when you turn off each feature. That level of transparency makes it easier for the whole field to build on these work. That's where we will wrap it up. One thing I'm curious about now is how fast companies will start using agents like this in real workflows. If CCA proves reliable at scale, it could change how large code bases get maintained. Drop your thoughts below. Make sure you're subscribed, hit the like button, and I will see you in the next one.